By the way, it's great to see a lot that I haven't seen in a long time, so I'm very glad to be here. Thank you for the organizers for inviting me.
Well, we're very happy to have you. So I'll make the proper introduction. We're very happy to have Erez Shochat from St. Francis, also my academic sibling, to talk about a survey on automorphism groups of countable, boundedly, recursively saturated models of PA. So go ahead, Erez.
Okay, thank you. And again, thank you for the organizers and for everyone who came. So I don't have new stuff to talk about, so I decided to just present on just do a survey on automorphism groups of both countable recursively saturated models and countable boundedly recursively saturated models of PA. Well, recursively saturated models of PA are already boundedly recursively saturated, but there are other models who are not recursively saturated models. They're just boundedly saturated, recursively saturated models. So I'll talk about the results on both, so let me begin. I assume most of the people in this talk know about recursive saturation. I'll go over it briefly. A model is recursively saturated if it realizes every finitely realizable recursive type with a finite number of parameters. So a result of Barweiss and Schliff, and also independently of Reser, every consistent theory in a finite language has a countable recursively saturated model. So as long as we have a consistent theory in a finite language, like a language of PA, we are guaranteed a countable recursively saturated model. But how many theories extend?
Sorry, Erez, you didn't say that we're allowed to interrupt at the moment, but this is
sure. Yeah, go ahead.
Yeah, tradition, so we're kind of rude. And anyway, so since Ken is here, I just want to point out, and he must have noticed that Reser is misspelled. But
yes, I did. I was going to save it for the end.
Is that with the E?
It's R-E, not E-R.
R-E.
R-E at the end.
Instead of E-R.
Oh, okay. I didn't know that. Okay, thank you. I'll change it in my slide after. So since there are continuing many different theories in a language, in the language of arithmetic extending PA, according to following from Gödel's results, there are continuing many different theories. So there are continuing many countable recursively saturated models of PA that are non-isomorphic and don't have the same theory. Moreover, each theory extending PA has continuing many countable recursively saturated models with different standard systems. So for every theory, there are continuing many standard systems. You can find recursively saturated models with different standard systems. So it's uncountable times uncountable many countable recursively saturated models of PA. However, that's the most we can do, because if two countable recursively saturated models have the same theory and the same standard system, they must be isomorphic. So still, we have a lot of these models. So the question is, what about their automorphism groups? So of course, if they are isomorphic, their automorphism groups are isomorphic. But what about the other way around? So if they have the same automorphism groups, does it mean that they must have the same standard system and theory? And the first question was, can we even find any two that are different? then are there any two models, M and N, that have different automorphism groups? So that was the initial question. And I believe until the 90s, in the early 90s, many results started coming. And we will discuss those results. A result that helped answer this question was the small index property. So just some notation: if M is a model of PA, we'll let G be the automorphism group of M, and then define a topology on G as follows. The basic open subgroups are the subgroups of the form G of A or GA. These are the stabilizers of individual elements. So GA is all the G's that fix A under the automorphism. So these will be the basic open subgroups. So we have this topology on the automorphism group, and we were able to mathematicians in the 90s were able to show that automorphism groups are some automorphism groups are non-isomorphic as topological groups. They needed one more piece to make it so that we can prove that they're not isomorphic as abstract groups. And that piece is the small index property. The M has a small index property if for any subgroup H of G, the index of H in G is countable if and only if the subgroup is open. Okay, so so that's a small index property. And if a model has the small index property, then if you can show, you can recover from knowing that two models are non-isomorphic as topological group, you can conclude that they're not isomorphic as abstract groups. So Lascar in '94 showed using generics. So I know Ermek talked about generics last week. Using generics, he proved that if M is a countable arithmetically saturated model, and I'll mention what arithmetically saturated means, of PA, then M has the small index property. Okay, so that's one of the results. And then just briefly, what is arithmetic saturation? A model is arithmetically saturated if for all A and B in M, let me just close the door here. No, it's okay. 1 second. A model M is arithmetically saturated for all A and B in M, if, not if and only, if for any finally realizable type whose set of Gödel numbers is arithmetic in type of A. So I just wrote this slide before so a model is arithmetically saturated if and only if for any finally realizable type whose set of Gödel numbers is arithmetic in type of A, so it is if and only if, is realized in M. So not only it realizes all recursive types, but it realizes finally realizable recursive types, but all finally realizable types that are arithmetic in the type of another element from the model. So it's a much stronger type of saturation.
Yes, so I just want to make a digression here, because last week when Ermek talked about it, he attributed the result here to Laurie, which was essentially right, and I objected because I said, well, Laurie couldn't have proved that because in the 70s, arithmetic saturation was not defined yet. But Jim went back to the paper of Barwise and Schlipf, which is, I guess, from 1976, And in the introduction, they say, well, you know, this is the arithmetic. There is a great importance of recursive saturation, but you know, if some people find this notion a little bit artificial, everything in the paper goes through if you assume arithmetic saturation. And the only thing, so arithmetic saturation was used actually by Barwise and Schlipf in the remark, but they didn't mean that. They meant arithmetic types. And it was quite often confusing that we're not talking about arithmetic types, we talk arithmetic types in the types that are already realized. That makes a big difference. Anyway, so arithmetic saturation existed, but wasn't really formally defined. It was just an offhand remark in this very important paper. It was Model Theory through Recursive Saturation by Barwise and Schlipf, I think from 76.
Yeah, but I think the notion of a strong cut was maybe used by Kirby.
Oh, not only used, but defined.
Yes, okay. So,
I guess what we didn't express it in terms of ACA 0 because that was not really yet defined either, or not really solidified.
If I can add into that interjection, I do think that you did say something about not so much ACA 0, but essentially what ended up being equivalent to ACA 0, namely that it's closed under sigma n definability or something along those lines.
Yes, absolutely. I was just saying we didn't have. I'm not sure if the concept ACA 0 had been invented yet, but we didn't have it yet.
Yeah, so these are just two equivalent formulations. I'm not going to go too much into them, but basically, just to remind you for n to be strong, it means that whenever you have an element E coding some sequence, there must be an element C such that E n for every n in n is in n if and only if En is less than C. So if that's true for every sequence coded of elements, we'll say that the standard cut n is strong in the model. So for every E in M, if we can, whenever it codes, every element which codes a sequence, we can find a C such that En is a standard number if and only if En is less than C. So so these are the some equivalents of arithmetically saturated. So it's a stronger saturation than recursively saturation. And using arithmetic saturation, the mathematicians, many of them here, were able to prove a lot of results in the 90s. So let's discuss some of them. In 91, K. Kozak and Kotlarski proved well, they proved this for topological groups, but together with the small index property in 94, it implied that if M is a countable arithmetically saturated model, and N is just recursively. So I just wanted to mention, just recursively means recursively saturated that is not arithmetically saturated. So it's a newer notion. I don't know if it's officially defined.
It is official at this seminar.
It's official in this seminar. Okay, so
Philip Rothmaler came up with it.
Was it ever like used in papers?
Now I think there might have been, but it's certainly used here.
Okay, great. So if M is countable arithmetically saturated and N is countable just recursively saturated, then their automorphism groups are different. So that follows from result of from the 91 paper, and together with the so they showed K. Kozak and Kotlarski showed that these automorphism group are non-isomorphic as topological groups, and then together with the small index property, it implied they're non-isomorphic. Okay, so also in 94, Richard K proved that if M is a countable recursively saturated model of PA, and H is a subgroup of G, then H is a closed normal subgroup if and only if H is the stabilizer of is a pointwise stabilizer of the of an initial segment of an invariant initial segment of M. So what does it mean? The invariant initial segment. So so here's M, and you have some elements. So an invariant initial segment is a segment that is fixed setwise. Okay, so let's say call this I, and f of I is I as a set for all, or G of I for all automorphism. G of I is I setwise. What is GI like this? This is the pointwise. These are all the G's such that G of A is A for all A in I. So it's not hard to show that this is a normal subgroup, but he showed that these are the only closed normal subgroups. Now, what are the invariant initial segments? So recursively saturated models are homogeneous, omega homogeneous. So that means that if you have two elements A and B that realize the same type, there's an automorphism moving A to B. In order for this to be invariant, the only invariant initial segments are those that have some definable elements, either cofinal in them. So this will be less than M of 0, or the M of 0 will be the largest initial segment containing all definable elements. So so for I to be invariant, it has to be either there is a cofinal I intersected with the Skolem closure of 0 is cofinal in I. Or the other way around. So there's a set of cofinal definable elements. There's a set of definable elements that are downward cofinal in M minus I. So so K showed that this happens, but what this implies is the following. If you have a model of true arithmetic, then there is no definable elements past N. So these are the only definable elements. So there are no non-trivial initial segments, or no non-trivial, automorphism really, no non-trivial normal subgroups. The only subgroups are closed normal subgroups, are the identity, which stabilizes the whole model, or all of G, automorphism of M, which all of them fix, of course, N. So so these are the only two if it's a model of true arithmetic. So if M is a model of true arithmetic, you have only two closed normal subgroups, the trivial ones. And of course, if it's false arithmetic, if it's a model yes.
A small digression. Can you go back to the previous slide? Because this is
you mean previous slide here?
Right. No, the
one I drew. What I drew?
Oh, right. Anyway, the case theorem that is, since you mentioned, I don't know if we're going to mention open problems. So K completely characterizes closed normal subgroups, but there is still an open problem to characterize normal subgroups as such, and we do not know if there are any. So
any other, you mean?
Any other. So maybe every normal subgroup is closed. But no, there is another one. There are those who there is this.
The greater than, I remember. This one.
And they might be the only two.
Right.
So this is the group that of those automorphisms that fix some initial segment that's larger than I. And so in the case of a model of true arithmetic, we know that those two groups, and we don't know any other. There are some conjectures, and I think those problems are difficult and somehow forgotten because people who work on it tried, but it's an open problem to see if there might be any other normal subgroups.
Yes, and I think that's called. I think we called it case conjecture. I think he wrote it in that paper about G greater than I. That he thought that maybe these are the only two.
These are the only normal subgroups.
Two possibilities.
Yeah, because the closure of E greater than I greater is the GI, and those would be one is not closed, the other is closed, and that would be all.
Yes. So again, from his from this theorem, it follows that since true arithmetic has only two invariant initial segments, N and M, and since false arithmetic has many non-standard definable elements, there are continuing many invariant initial segments here. While here there's only two, and therefore they have different closed normal subgroups, so they're not non-isomorphic as topological groups. But in particular, again, because of the small index property, for arithmetically saturated models, these two models have non-isomorphic automorphism groups. Although probably if what we mentioned about the other result is true, then we don't even need the small index property will be true also for just recursively saturated models. Okay, other results about automorphism groups and now we're going to start getting much more. So far we got a few distinctions, right? So let's just go back for a second. We had the distinction between countable arithmetically saturated and just recursively saturated, but nothing more than that. And then we had this, and actually I gotta say that there are other cases that maybe I didn't mention, but very small distinctions. In the next slide, we start getting more distinctions, or really continue many different automorphism groups. So this follows from a result of Kozak and Shmerel from '95, which says that if M and N are countable arithmetically saturated models of PA, and their standard system is not the same, and as I mentioned, there are continue many different standard systems, and some of them are arithmetically saturated, some of them are none, there'll be continuum for each. So whenever you have two countable arithmetically saturated models of PA with different standard systems, then their automorphism groups are going to be non-isomorphic. So again, that produces continue many countable arithmetically saturated models with different non-isomorphic automorphism groups. Okay. So I think after this result, the next question was, okay, what about the theory? So remember in the beginning we said two models are isomorphic if they have two recursively saturated models are isomorphic if they have the same standard system and the same theory. Well, now after this result, we know that if they have different standard systems and they're arithmetically saturated, they don't have the same automorphism groups. Now the next question was, what about different theories? Sometimes you can have different theories and the same standard system. So what happens in models that have this different theories? Are they non-isomorphic? Can we show that they're non-isomorphic? So the first positive result, yeah, was by Ermek Nurkaidarov. Correct me, Ermek, if sorry for misspelling your name or mispronouncing. Nurkaidarov.
Very good.
In 2006, found four complete, I think he found it a little before, but I think it was published in 2006, 4 completions of PA, such that whenever M and N are countable, arithmetically saturated models of 2 different theories of the above 4 completions. So we have 4 different completions of PA, so 4 different theories. And if you take 2 models, 2 countable arithmetically saturated models of these theories, then their automorphism group is non-isomorphic. Moreover, we can always find such M and N, which in addition have the same standard system, as I mentioned. So they have the same standard system, but they still have, you can find 4 different theories with that standard system, and none of them are isomorphic to each other. In 2015, Shmerl proved, extended it, again, I'll correct that, proved once, that the number of theories in the above theorem can be extended from 4 to continuum many. So we got, using Turing jumps of the theories, and it's a little bit hard for me to understand the proof, but using Turing jumps in the theories, and he was able to show that there could be for every, I guess, standard system, continue many theories that have the same standard system. They're arithmetically saturated and they are non-isomorphic. Yes.
Another digression. You did give us a talk on this.
I did, but it was still hard for me to understand it completely.
No, it was hard for you and it was hard for everybody else. But I think this is a wonderful paper. Jim comes with a wonderful paper one after another. But this one, it's really a wonder of, essentially it uses all techniques about non-standard models of PA that we know about, most of them, in the single paper. And it's not that well known partly because it's difficult and not that many people are interested in the area here anymore. But it's just a wonderful paper, and so it leaves an open the question that perhaps you would mention it, that fine, there are continuum many, but they are very specific. Mm-hmm. So the question is again open whether there could be models with distinct first order theories and isomorphic automorphic group. This question is wide open because these theories that Jim produces are very specific, but extremely interesting.
Right. So it's not, it doesn't cover everything. It's not, you remember the previous result from 95 of you and Shmerl said that if they have the different standard system, then the automorphism groups are different, are non-isomorphic. But this one doesn't say that if the theory of M is not the same as the theory of n, and they're arithmetically saturated. That we don't know. So I would put question mark. I mean, if that would solve, I think that would really put an end to all the questions here. That's like the last one. If you have two different theories, well, not the last one, because the just recursively saturated is completely open. So this is all for arithmetically saturated, but for arithmetically, this would be probably the last question. If you start with two different theories, does it always imply that the automorphism of M is not the same?
No, and because it's a late night seminar, at this late night seminar, I would conjecture that this cannot possibly be true. That automorphisms cannot possibly know all theories extending PA. They know something about those theories that Jim concocted. They're specifically designed to do what needs to be done. But to have somehow and the arbitrary information about, no, because there's you get many completions of PA by just completely random process through a binary tree, you know, with many branches. And how you know, that I don't think that, you know, the automorphism group that, you know, it's quite sophisticated, but it cannot know all of those paths through the tree.
So I guess the other question would be, can we find M and N?
Right.
Such that the theory of M is not the same as the theory of N, but still they have the same automorphism groups.
Right, and we don't have a single example.
Yes.
One thing about this result of Jim's here, he mentioned Erez about how he uses it has something to do with the string jump. He is able to say something along the lines of, if two models have the same automorphism group, then you do know. So it's not just that he concocted certain theories. You do know, in fact, that the two models have theories which are Turing equivalent. And so if you were to try to prove a result along the lines of what you were alluding to, build two models with different theories that had the same automorphism group, you would have to start with two models with where their theories were Turing equivalent. And so there is so somehow the automorphism group does know something about the theories, but perhaps it doesn't know everything.
Yeah. So definitely open questions here. Now, the other side, as I mentioned, is completely open. Not completely open, but there's a lot that we do not know. So the question is, can we actually do something similar with just recursively saturated to show that if they have different standard system, then their automorphism groups are not isomorphic? So that's an open question that I didn't list at the end, but it's definitely something that we want to investigate, and of course with the theories as well. Can we do something similar with just recursively saturated? Okay, so that's for the first part of the talk, and the second part is something that I worked on for my dissertation, and as you see, there's so much more open, and I believe could be solved, at least some of it, in the next few years, I hope. But let's see what is already known. So what is bounded recursive saturation? And in old terminology, it used to be called short recursive saturation. It's a little, I guess, like contradictory definition, because recursively saturated models are not short. So I think Roman and Jim suggested boundedly recursive saturation instead of short recursively saturation. But if you go to old papers, you'll see short recursively saturated saturation more. I will still use the word short recursive saturation, but I'll for this talk just to distinguish between the ones that are recursively saturated and the ones that are not recursively saturated. So a type is said to be bounded if it contains the formula V is less than T of A for some Skolem term T. So so V is bounded by some Skolem term T, so it will be realized somewhere below A. So it's bounded. So another way of thinking about it, somewhere below T of A, sorry. A model M is boundedly recursively saturated. Again, in the past, it used to be called short recursively saturated. We term it now boundedly recursively saturated. It's boundedly recursively saturated if it realizes every finitely realizable bounded recursive type. So just one more condition, the type has to be bounded. So boundedly recursively saturated models realize every bounded recursive type with the finitely realizable type, bounded recursive type with a finite number of parameters. So some observations. Notice that every recursively saturated model is boundedly recursively saturated. That's why I called my talk a survey on boundedly recursively saturated, because everything I talked about was a special case of the boundedly recursively saturated. This was the recursively saturated models. But in this part, we'll talk about the boundedly recursively saturated that are not recursively saturated. So notice that every recursively saturated model is boundedly recursively saturated. Question: which boundedly recursively saturated models are not recursively saturated? And the answer is these are exactly the short models, the models that have a, well, let me define it right here. A model is short if for some element in the model, the Skolem closure of that element is cofinally in M. Okay, so basically every X in M there is a T of A Skolem term that is bigger than that model. So Skolem closure of A is cofinally in M. For any model M, let M of A, and this terminology was used in different papers differently, but I'm going to stick to the old terminology. I don't know if there's a new terminology really for this, so I'm just going to use the old one. I know that MA was used for two different things, but I don't know if this had a short another way of writing it in the context that I'm talking about.
So this was something, the time-honored notation that was used by Kotlarski in many papers, and then it only clashes with Geifmann's. This sort of a different branch of model theory of PA, when this just denotes a model that generated by M and A. And there's problem. But once you're in sort of, so I like this old notation. With Kotlarski's notation was fine.
Okay, good.
No, you can just, there have been attempts to change it, but I think this is no one is confused.
Okay, and I put the definition here. So yeah, so let MA be the smallest elementary initial segment of M containing A. So now it's not only Skolem closure of A, but everything that is below and or equal stuff in Skolem closure of A. So that's M of A, the smallest elementary initial segment containing A. It can be shown, again, these are fairly straightforward. X is less, MA is all X's that are less than or equal to T of A for some Skolem term A, Skolem term T, sorry. Clearly, MA is short because Skolem closure of A is a cofinal in M, or sorry, MA is this model. Column closure of A is by definition almost. Also, MA is not recursively saturated. Short models are not recursively saturated, and it's actually it's a very easy observation, or for the people here, is just you write a type V is greater than T of A, and this type for all column terms, this is a recursive type. T is a column term. That's a recursive set, and it's finitely realizable, because if you just take finite of those, there is an X greater than these definable. Just add 1 to the max. So you know, this is realized in the recursively saturated models, but it's not realized in MA. So MA is not recursively saturated, and this is again if M is recursively saturated, you can show, I think that's my next slide. If M is recursively saturated, then MA is boundedly recursively saturated. I think Smorinsky proved it in '81. Again, fairly simple, but argument using the definition of bounded recursively saturated. So if M is recursively saturated, then MA is boundedly recursively saturated. And if M is boundedly recursively saturated and M is tall on the other hand, then M is recursively saturated. So if you start with a model that is recursively saturated, but you show that it's tall, that's also a proof of Smorinsky, then M is recursively saturated. So let's try to make sense of everything. I have a slide with that, but let's just make sure that we understand what's going on. So if you start with a recursively saturated model M, you put an A here, look at column closure of A. There'll be stuff that A defines maybe below. Of course, definable elements are in this column closure, but then there'll be stuff here. But because M is recursively saturated, A is not cofinal in M. Basically, M is tall. Recursively saturated models are tall. But if we look at the initial cut, the elementary initial cut that contains A, again, that's MA. This is just boundedly recursively saturated. It's short, so it's not recursively saturated, but it's boundedly recursively saturated, and it lives inside M. If you take any boundedly recursively saturated, so that's a different picture. So you start with a boundedly recursively saturated model. If you can show that it's tall, then it's possible, then you can prove that it, or if it is tall, then it is recursively saturated. So basically you have two options. A model is either tall or short. There's no like in the middle. So if a model is I didn't even say what tall is. Tall is not short, basically. So if a model is tall, so if M is boundedly recursively saturated, there are two cases. Either it's tall and then it's recursively saturated, or it's short and then it's in the form of MA for some element A in the model. Okay.
Erez, so what
Yes.
you just said, you didn't have that on the slide. This requires a separate proof.
Probably. I have some in this slide. Maybe I have some more stuff that maybe that's, yeah. So maybe that will be, I don't know if that's there, but I know I wrote more stuff. So maybe I said it, but I also have it in this slide. But which one are you talking about that requires more proof? That if I have that, if it's short, it has to be the form of MA. Not sure which part. are you referring to? But let's see this slide. I think it repeats what I said in this slide. So if M is a countable recursively saturated model of PA, M has continuum many elementary initial segments. So it takes it a little further. All but countably many are recursively saturated. And all the recursively saturated are isomorphic to the original model. So yeah, that's a different thing. So I don't know. It does require a different proof, I believe. I just
this is something general about recursive saturation. But what I said, that if you just have a short boundedly recursively saturated model, and that it actually has an elementary end extension to a recursively saturated model.
Yes. Oh, yes. So I do have that slide. Yes, I do have that result in a separate slide. Yeah. Yes, correct. And it's a result of you. That's your result. So I do have it. Remember, I think it's the next slide, next page.
Jim also proved it at the same time, as always happens. You know, Jim proved everything, but he didn't push. But I didn't know about it.
And Smorinsky proved it in the countable case, I think.
Right. And I did the uncountable.
Yes, right. So I have that slide in it. Yeah. So let's so now let's look at the countable recursively saturated model of PA. It has continuum many elementary initial segments. So so that's quite big, but you can prove it using cuts of rational. So this is so it has continuum many elementary initial segments. All but countably many of them are recursively saturated, and all of the recursively saturated are isomorphic to the original model. Why are they isomorphic? Well, that's because of the results that we had before. If you start with M and you have a cut N that is elementary, and it's recursively saturated model, they have the same standard system. So they have the same standard system. But if they have the same standard system, they have their elementary initial segments, so they have the same theory. They're both recursively saturated models, so they are isomorphic to M. So you have continuum many models, elementary initial segments that are isomorphic to the original model. Okay. The elementary initial segments that are not recursively saturated are still boundedly recursively saturated. Again, you could prove that. And in fact, they're all short in the form MA for some A in M. So I think the result is here. Yeah. Okay. Just again about the terminology. I'm going to call the short boundedly recursively saturated models. So these are the recursively saturated models that are not. So these are the boundedly recursively saturated models that are not recursively saturated. I'm going to just call them short recursively saturated instead of short boundedly recursively saturated, just for short. So as we just met, no, that's not this result. Yeah. Smorinsky in '81 proved using a back and forth argument that two countable short recursively saturated models, MA and NB, are isomorphic if and only if beginning is the same. Theory of M equals the theory of N. Standard system of M equals standard system of M. But also we need that there's a C, an element in gap of A and an element in the gap of B, which realize the same type. And then you can really send C to D and isomorphism preserve gaps, also automorphism preserve gaps. So you'll send, you start by sending C to D and you can do back and forth. And these are isomorphic.
You didn't say what gaps were.
Oh, I didn't say gaps yet. Yeah, I'm sorry. So it's coming up, but let me just say it since I mentioned it. So we talked about a MA, which is the initial segment that contains the largest initial segment that contains A, but there is another initial segment, MA, sometimes we write it like this, which is the largest initial segment, elementary initial segment, that does not contain A, which means that if you have an element here, that element already can go past this by like you can define from here something there. So this is the largest initial segment that contains A. This is the smallest initial segment that contains A. This is the largest initial segment that does not contain A. So the region between those two is called the gap of A, sometimes with a capital G, sometimes lowercase g. It's all the elements such that either T of X is greater than A, sorry, both T of X is greater than A. So it's all the X's such that there exists a Skolem term T such that T of X, because X, T of X is greater than A, and T of A is greater than X. So it's whatever A passes by some definable Skolem term and whatever passes A. So this is called the gap of A, and gaps under automorphism, under isomorphisms are mapped into gaps. So if A goes to B or C, it doesn't matter, then the whole gap is going to go right there. So that's the result of Smorinsky, and then I want to run out of time. It follows from the above results, and the results of Geifman, because some gaps do not realize the same. Not every gap realizes the same types. Some gaps realize certain types. Some gaps realize different types. Some types are minimal types. Some gaps have no minimal types in their gap. Some have a minimal type or minimal types in their gap. So from results of Geifman, it follows that every countable recursively saturated model of PA has countably many non-isomorphic short elementary initial segments because their last gap. So a model like this, a short model, has a last gap, and the last gaps don't have elements which realize the same type. So you can't map one into the other, and they are non-isomorphic. Even if you have the same theory and the same standard system, well, and in particular, if you're initial segment of the same model, you'll have countably many non-isomorphic initial segments. And here's the result that we mentioned: Smorinsky in the countable case and Kozak in 83 in the general case for all models, and I guess unpublished Schmerl also proved that every short recursively saturated model of PA has recursively saturated elementary end extension of the same cardinality. So that will complete what I said. So if you start with MA, there must be, well, we don't call it MA. Well, we could call it MA. There will be an N extending elementary N extension of that is recursively saturated. So this will be short recursively saturated. This will be recursively saturated. Okay. I'm trying to get to the automorphisms. Therefore, when we study non-standard short recursively saturated models, putting it all together, we can think of them as in the diagram below. You have the standard, so this is the standard N. So the standard elements, and then take a non-standard element A and look at its largest initial segment containing A, and that's called MA, and it lives inside a short recursively saturated model, lives inside. And by the way, I put here non-standard. It's an old slide that I recycled or reused. I put non-standard because technically the standard model N is short recursively saturated. So maybe we should, exclude that somehow. We could keep that, but when we study the non-standard recursively saturated, short recursively saturated models, we can think of them as in the diagram below. Next, so now I think I have the definition of gaps. Oh, I can't. Oh, that's a different mark. Oh, I see what I did. For the rest of the talk, let M be a countable recursively saturated model of PA. Let A be an element of M, and MA is, and as we said, MA is a short recursively saturated model which is not recursively saturated. Or just as we said, short recursively saturated will mean that already. And let the gap of A be exactly what I defined before. Okay, so this is the picture, but I was thinking about it. This is not a true picture. So I just wanted to make a comment because I always write it like this, but the true picture is really remarkable. You have that standard model right here, or standard elements. And then if you take a non-standard element, it's much, much bigger than all these. So if you have A here, then first of all, if you look at MA, this part, the smallest initial segment not containing A, it's much, much smaller than anything that is, it's much smaller than half A. It's much smaller than any billionth of A. So A is, so if this is here, this is like the gap of A is much, and this parenthesis is much, much bigger than A. It contains all the A to any powers and things like that. So all these gaps, we sometimes redraw them like this. We have these gaps, but actually the sizes are none. You can compare them. It's really like this is almost infinitesimal compared to what you have here. It's not drawn to scale. Let's put it this way. So this is the picture, and so we have the gap of A here. And let's now move to talk about automorphisms. So a quick fact, and this I wrote in the last minute, so I didn't, unfortunately, I didn't have a chance to correct the font. So again, remember, M is now recursively saturated. Every recursively saturated model is omega homogeneous. In particular, if you have two elements that realize the same type, then there's an automorphism sending A to B. MA is not, because if A is in the last gap, excuse me, and B is here, as I mentioned, gaps have to map to gaps. There's no automorphism of MA that sends A to B, because this gap is the last gap. It has to move to itself. So if B is in the last gap, yes, but if B is right there, then it does not. So it's not omega homogeneous. Let G be an automorphism.
Can I ask a question here?
Yes.
Is that the only restriction to homogeneity? So in other words, if you look at any two elements in MA that are not in the last gap but do have the same type, is there an automorphism between moving one to the other in that case?
I'm pretty sure yes. So if you have, so yes. So
no, don't go there.
No.
This is the essence of the moving gaps lemma. You can have a C down below such that
You
if
have to move that. Yes.
if you move C anywhere, you have to move the whole
Right.
gap.
You have to move the whole gap. Right. So yes. So the question. So it's not the only restriction.
And
So
this
you could have two elements here
right.
that are outside of this, and any automorphism that moves A to B will have to move this gap, and therefore it's not going to be possible. So yeah, it's not enough. What is true though, if you can find a C in the last gap, so let's call this a D because this is the gap of A. If you can find a C in the gap of A, in the last gap, such that the type of, or even a C and a E, if the type of B, DE, DC, for example, is the same as the type of a BE, then yes, then you can do that. So you need to find two elements in the last gap that will work as fixing that gap, not point or setwise, because then if the type of DC is the same as the type of BE, then there's an automorphism sending a, well, really it's an automorphism of M sending a D to B and C to E, but because it fixes the last gap, it will be an automorphism of MA. So what we'll need for that, we'll need to find elements in the last gap that serve as like a, I guess, almost like an anchor to keep the gap in the same place.
Right. And I just want to say that, you know, this was Kotlarski came up with this moving gaps lemma, and this was really a beginning of many important developments after that, because it's not intuitive. Okay, because you think, oh, it's a recursive desaturated model, it's omega homogeneous, all kinds of things work smoothly. But Kotlarski says, well, wait a moment, it's not really like that. There are some unexpected things that happen. Moving gaps lemma is somewhat unexpected.
Right.
So it shows that, for example, you cannot move things locally. You cannot have an automorphism that only move elements of a gap to the same gap. You would think, why not? But I can make this sort of small moving automorphism, but it cannot happen. If you move anything, that you have to make some large leaps about it. You have to move the whole gap to another gap.
Mm-hmm. Yeah. Okay, so let G be an automorphism of M, which fixes the gap of A setwise. Then the restriction of G to, that's what I just said, the restriction of G to MA is an automorphism of MA. So as long as you have, so you start with any automorphism of M, which fixes MA or gap of A, well, setwise, which in particular I will fix MA setwise. It's an automorphism of MA. Are these the only automorphisms? Well, it turns out that they're not. Right, so as I mentioned, we said more than that, so let me skip that, let me continue. The automorphism of MA contains many automorphism, don't need that, which can be extended to automorphism, which cannot. Well, continuum many can be, but continuum many cannot. So that's the next slide. Are there any automorphism of MA which cannot be extended? And the answer is yes. So I was able to prove it in 2006 using a construction that was suggested by Roman. There are continuum many automorphism MA which do not extend to an automorphism of M. Okay, so so the idea was, again, without much details, if you have MA here and you have the gap of A, then you can find a set. So the construction was finding a set X here that is coded by some element here outside of M, outside of MA. So as an automorphism of A, if you look at an automorphism of M, there are only, M is countable, there are only M countably many images of B. But that means that X will have countably many images, but that set was constructed in a way that in MA, it can be shown that it has continuum many images. That's using the Erez lemma. I was able to show that it has continuum many images here, but only countably many under automorphisms of M. So so that's a result that was proven. And then another result is an extension, or not extension, K's theorem for short recursively saturated models, using similar arguments to K and making sure that things work. Have to be a little careful because we don't want to move the last gap. But I was able to show that the closed normal subgroups of the automorphism group of the countable short recursively saturated model of PA are exactly the pointwise stabilizers of the invariant initial segments. However, for short recursively saturated models, there are sometimes, not always, sometimes there are, well, definitely there's one more, but sometimes there are continuum many, or continuum countably many. Could be continuum many more invariant initial segments. So if a countable short recursive saturated model of PA realizes a rare type, so how can we find more? So here is the idea. So you're in MA, and A is somewhere here, and this is MA here. So we're here in the gap of A. If the model realizes a rare type, so suppose, let's use a C, not A. Let's suppose C realizes a rare type. What does it mean, a rare type? It's a type that is only realized once in this gap. So since this is the only element that realizes the type of C, only C realizes type of C in this gap, then no automorphism of MA, since it has to fix this set-wise, it has to send C to C. So every automorphism of MA sends C to C, but then it fixes a lot of stuff. It fixes C+1, C+2, etc. It fixes 2C, 3C, C squared, etc. So what we get from that is all these continuum many invariant initial segments in the last gap, and they're cofinally high, and that could be used to show that the normal subgroups of a model like this is different than the normal subgroups of a model that does not realize rare types. So then every C can move, and then if it can move as high as you want and as low as you want, and there are no invariant initial segments, and therefore the closed normal subgroups of the automorphism of a model like this will be different than a model that does not realize rare types. So if it does not realize a rare type, then you'll have no invariant initial segments in the last gap. So it's a big difference, and the implication for the closed normal subgroups is big difference. So countable short recursively saturated models of PA which realize rare types in the last gap, and countable short recursively saturated models of PA which do not realize rare types in the last gaps have non-isomorphic automorphism groups as topological groups. So unfortunately, we don't have the small index property yet for a short recursively saturated models. So we cannot conclude that they're non-isomorphic as automorphism groups, but just as topological groups. Sorry for the ambulance. So done, just some open questions. So the main question for this one I mentioned already before. This is for the just recursively saturated models. Do they have the small index property? And also, can we apply can we find the similar results that we did for the just recursively saturated models as we did for arithmetically saturated? But what about short recursively saturated models? Do countable short recursively saturated models have the small index property? That would help. That would prove that those two models are non-isomorphic as the automorphism groups are non-isomorphic as abstract groups. Do different standard systems imply different automorphism groups? So can we do something similar to the proof of Kozak and Shmerel from '95? There is one difference that I was able to show in a paper in 2010 for short arithmetically saturated models versus just short short arithmetically saturated. So it's the equivalence of short recursively saturated model, but just standard system has that property as arithmetically saturated models versus just short recursively saturated or short just recursively saturated models. They do have different automorphism groups as topological groups, though. So I should say as topological groups. Again, small index property will bring it to as abstract groups. And finally, do different theories imply different automorphism groups? So do different theories imply different automorphism groups? And again, for model of, so I think the question for theories for short. So I should have said for short, imply different for true arithmetic versus model of false arithmetic. In some cases, again, because of that result that case theorem closed normal subgroups in the short case. Okay, so a lot of open questions, and but there are a lot of results, especially for arithmetically saturated models. But the hope is now maybe just recursively saturated models, to have some results, and for short recursively and short arithmetically saturated models. Okay, so that's the end of my slides. Thank you.
Okay, let's thank Erez. Thank you for that. That was great. And if there's any questions, feel free to speak up. I have one or so I was actually about to ask, but then you said something about it. I wanted to ask, as you were talking, I started thinking what is known about the short version of arithmetic saturation, and then you showed a result there, which is interesting. Is there anything else known? And is this notion studied in at all beyond sort of some? Are there any other nice analogs to what we know about from arithmetic saturation?
Not yet. I think a lot of these arguments, they have to be worked out, step by step, see if it works for, and there's some things that we have to be careful, as we mentioned, because you can't just say, oh, it's just a, it's just a subset of the automorphism group of M restricted
Right.
to, because there's continuum many that do not extend. So
Right.
there's some things, but some things there's some shortcuts where you can find an element in the, or you can fix the language. Sometimes, one trick that in some proofs works, sometimes not, is to say, well, I guess especially if A realizes a rare type, but so it has to be fixed in the last model. But maybe we fix A in the language. So A is part of the language, and then M is still recursively saturated, and then we now all the automorphism of M are restricted to MA, our automorphism of MA, and since M is in A is in the is fixed in the language, but if A is in the A realizes a rare type, then I think that would be A will have to be careful about that. But definitely we can work with this. Say, okay, this is a recursively saturated model in the language with A as a constant in the language. Take the results and then see if we can then argue this for MA. Because so that was something that I was able to use. For the other result, let me see if I have the other paper. I think I had the paper some. Where is it? I think it was in this paper from 2010. Sorry for the compound interest slide. But the result was for the short arithmetic saturation. So if you want to see more, I don't know if it was ever like really treated besides this paper. So this is a mathematical logic quarterly from, what is it, 2010, volume 3, I think. So here I have those definitions, and that's where I prove, again, using the results I think I extended from that paper from K. Kozak and Kotlarski. I think that's where I did a similar. I showed that it applies, and therefore it was. Oh, I'm not sharing, am I?
No, you stop sharing.
Yeah. Okay, because I thought I was sharing. Yeah, but this is. Oh, so let me share again. Yeah. So this is the paper, and yes. So if N is strong in MA, if and only if there exists an automorphism and an open subgroup H in G of A, such that for every F, the conjugate F inverse GF is not in H. So this is true if and only if, and it's about open subgroups, and from that is a corollary, and that's the result that again K. Kozak and Kotlarski proved for the recursively saturated models, and then I applied it to the short case. Yeah, the above result is true, and it was proved by K. Kozak and Kotlarski. And then the corollary was let M1 and M2 be countable short recursively saturated models, and suppose that M1 is short arithmetically saturated, M2 is not, then automorphism of M1 is not isomorphic to automorphism of M2 as topological groups.
Yeah.
Yes. So.
Very nice.
Yeah.
Erez, so I think Attar's question is a good one. because there are many things one could try. I was thinking about the characterization of arithmetic saturation in terms of existence of maximal automorphisms. So you can ask, when does a short recursively desaturated model have a maximal automorphism? And maybe, there's some chance that it might have, because if the standard system is closed under arithmetic saturation, if the initial segment is strong, then it extends to a model that's recursively desaturated, and it has to be arithmetic desaturated. But maybe there is a maximal automorphism of a shortcut that fixes only definable elements, but none of those can extend to this arithmetically saturated extension. I think this is probably unlikely, but it would be interesting to see if one can actually prove it. That characterize short arithmetic saturation in terms of maximal automorphisms, and then there might be, but this is one of the most natural, sort of the easiest formulation. It is something if and only if there exists a maximal automorphism. It would be interesting if it holds in the short case.
Yeah.
Maybe you need to try that.
Yes, yeah, definitely something to look at.
Ermek, do you know anything about it?
I actually had a slightly different question. I believe you and Jim, when you were doing your coding of standard system in arithmetically saturated models, you used unbounded elements.
Very much so.
And it was shown that you actually can do that in the first injections.
Well, that I think you did. You tried that.
I believe it will be true. So if it can be done in the first injections, that might imply, positive or whatever negative answer to that question number 2, which was on the list of errors.
I see.
Nice.
Right.
That would save time, definitely. So one more thing that I wanted to mention that you reminded me about results was the invariant initial segments. So as I mentioned, there was a rare, if A realizes a rare type, then you will have a lot of invariant initial segments here. But sometimes A also defines elements here. So then you'll have invariant initial segments there. And the question is, how do they relate? Are they cofinal? Well, they can be really cofinal here. But how do they, and I think it depends on the type. There's quasi-selective types. I remember in your paper, Roman, with I think it's the same paper, or maybe a paper with Shmerl and Kotlarski.
Kotlarski, yeah. Cool.
Yeah, where there were some elements A's that defined elements below, and then in column closure of 0, M of 0. But then there were ones that only define stuff here and there.
Right.
So I don't know if that would imply different invariant initial segments, and maybe we can find using
right. That would make a difference, probably.
Yeah. So that's another place to investigate. So there's a lot to investigate.
I want to say thank you very much,
thank you,
Erez, for the talk, because it brings all those memories. I think these are all kind of very nice things to think about, and kind of elegant techniques, and sort of revealing some unexpected properties. But this whole project has stopped because things became difficult, and Jim and Ermek proved things, and you can push things a little forward, but it becomes hard, and especially in the just recursively desaturated case, no one knows anything about it, and it's a little bit of a it's a shame. But also another interesting thing that I hope that perhaps someone can maybe explore a bit is that it all works nice for Peano arithmetic and extensions on, it all works for PA star in countable languages. This is not just PA, but if you go to fragments, nothing works. There is nothing really known about, recursively desaturated automorphic groups of models phi sigma n or I delta 0. There are no analogs of these results at all. So perhaps it would be nice to have some explanations why you need to go to the whole strength of PA, when you can talk about arbitrary induction for the terms of arbitrary complexity and things like that, and things work fine. But if you have anything less than that, things break down, or at least no, we cannot do anything about it.
So Roman, can I ask you then, is there other questions, are there things known about automorphism groups of expansions of models of PA? And I'm thinking right now about like models of CT minus and you know, models with truth predicates that might not be inductive.
That is a question to ask Bartosz when he comes next week.
Yeah, because I would suspect that similar issues with you know, basically any time that you lose induction, I expect you'll have similar issues. So even if in the expansion.
Right. Now, there is a wonderful result of, you know, this was actually proved by Smith, that if you have a full satisfaction class, that it defines an undefinable class.
Right.
But Bartosz showed that actually it defines an inductive partial satisfaction class. So it somehow goes. So you have in when you have, you know, if you have so much information as the full satisfaction class carries, that inside it there is already a definable partial inductive satisfaction class. So some of those things must be happening there because of, you know, at least part of the language that allows you to do things. But
right.
There is something beyond it, and I'm not quite sure how much control over it there is. No, that's a big.
And another question for me. Do you know if short saturated models have the small index property? Is this something?
This is for Erez to find out.
So yeah.
Okay, because that seems like a natural hope, I would say, that you could hope for that, and then maybe get some of those results would translate down, because you know you prove something about topological, you know, not being isomorphic because topological and things like that. So that might be a sort of.
So this is something Erez said something about it already. That, you know, in my group, you know, I think in the original group, and you know, and then
it's unbounded.
That you actually need something like Geifmann's minimal types that help, and you need to be able to talk on unbounded types. And when everything's localized, you don't have that unless the smallest interstices where some things, the intricate things are happening. But it becomes complicated, and that's also a problem with fragments. There are no definable types, no minimal types of fragments of arithmetic. So you cannot use this machinery to prove things. Actually, no, this is a combination of recursive saturation and this whole machinery of minimal types that works nicely.
Right.
But if you don't have it, then you have to come up with some other techniques that we don't have. But there might be some.
Right.
I have a question which may be elementary. This thing about the standard part being strong characterizes arithmetic saturation for the entire model. Is there a property of the standard part which characterizes recursive saturation or bounded recursive saturation?
No. No, because every model, you know, because the same standard system can be a system of minimal extension of the standard model. You can have the same standard system with a model that's as non-saturated as you imagine. So it can be just generated by a single element. You know, this is the result that I like very much. This is actually due to Jim, that every model of PA has a super minimal elementary extension, which means an extension just with one element, such that the column closure of that one element is the whole model already. So you have the same standard system, but absolutely no saturation.
It would have to be a property of the standard cut which went beyond the standard system, some other property of the standard cut in the model.
But are there any that go beyond the standard system? Right. No, that's
some undefinable property.
Oh no, but yeah. No, but this would be a property that's not that somehow that can be violated by making an elementary end extension. So What kind of property? But maybe there is some property of the standard cut that is not localized, arbitrarily low. Maybe there is some, but I don't know what would it be. Because everything depends on what happens just above the standard cut won't be altered by an elementary end extension.
But somehow arithmetic saturation refers to the entire model.
That's true.
Even though strong does not.
But under assumption that you are recursive saturated to begin with.
Right.
I think maybe in my slide I didn't put that M has to be recursively saturated, and then this is the if and only if. If M is recursively saturated, then if it is strong, it is arithmetically saturated. Not just being strong. So I neglected that here. So it's recursively saturated and N is strong in
being strong does say something about the standard system even without saturation. Is that right?
Right.
And so yeah, so it is truly a different type of model, because recursive saturation, you don't really have any control over the standard system. So you would need a property.
But at the same time, what I think the correct way of thinking about recursive saturation, that is really standard system saturation,
right?
For rich theories,
right?
It's much more than recursive saturation, but it's very closely tied to the standard system.
Right. Okay. Any other comments, questions? All right. Let's thank Erez again. So thank you. This was great. And I'll stop the recording here.